Here's a particularly strange variant of a power law. It's not exactly Zipf's law, but it's so bizarre that I can't resist talking about it for a little bit. It's also slightly more interpretable than other domains, so we can at least get a glimpse for what's happening behind these power laws. So, Benford's law. So, Benford's law is a really weird empirical law that says that if you take a large collection of naturally occurring numbers, so for example, constants in physics, or population numbers across countries or cities, and then in this big collection of numbers, you look at the first digit of a number, right? Just the first digit, ignores the rest. And then you plot the frequency of the first digit of a number. Now you would expect the frequency to be uniform, but it's not. That's what it actually looks like. So the green line in the graph, that shows the frequency of the first digit in physical constants. So what you see is 1 is by far the most frequent first digit of a number in physical constants. 2 is less frequent, 3 is less frequent, and so on and so forth. There's some variation, but in general, that's how the numbers fall down. So Benford's law says that the numbers would follow approximately this function. So it's a strange function, it has a strange parameter in it, but d is the value of the digit, right? So that's what it looks like. It gives the highest probability to the to digit 1, lower to digit 2, lower to digit 3, and so on. Again, empirical law, strangely enough, you see it in lots and lots of different places. You see it in electricity bills, you see it on stock prices, you see it in population numbers. Why on earth is this happening? Am I lying to you? No, I'm not lying to you, and it is. But the first time you see this law, that's a natural reaction. It's like this doesn't make sense. Why do numbers have this pattern to them? The particular trick here is it's not just any numbers; it's naturally occurring numbers. So if you generated a bunch of random numbers, this wouldn't be the case, right? For random numbers, you'd actually get a uniform distribution, right? Now, what's true about naturally occurring numbers is a lot of the time they have exponential growth patterns, right? So imagine populations, city populations, or if you prefer populations of rabbits, right? So you start with 2 rabbits, and before too long you have 4 rabbits, and before too long you will have 8 rabbits, and 16 rabbits, 32, 64, and so on. So that is a quantity that grows exponentially with time. And it doesn't just happen with rabbits, it happens with I guess the easiest example is perhaps city populations. If you have a large city, its population is going to grow more rapidly than a population of a smaller city, on average over a long stretch of time. And the reason this happens is that the growth will actually be proportional to the current size of the city, right? So if every family has 3 children, then it will grow by a certain amount in a certain amount of time, right? So any time you have an exponentially growing quantity, something interesting happens with the first digit of those numbers. So this is a little graph showing an exponentially growing quantity. So what I'm saying is the x-axis is time, and the ticks that I'm putting on it are the values of, let's say, a population of something. Right? So let's say that this is a cell dividing in some organism. So you start with 1 cell. And a certain amount of time later, it's going to split into 2 cells, and then, so it's not actually going to split into 3, but then the same amount of time later, those 2 cells are going to split into 4 cells, and so on and so on. The basic property of an exponentially growing quantity is that it takes a constant time for the value to double. So the amount of time that it takes to go from 1 cell to 2 cells is the same as it takes from 2 to 4. And it's the same as it takes from 10 to 20, and it's the same as it takes from 100 to 200. Okay? So how is that connected to Benford's law? It's connected if you look at the amount of time, right? So suppose you observe this process and you try to measure what proportion of time is the first digit, digit 1. Right? And that time is that, right? So it's 1 as long as it takes for a single cell to divide into 2. It's 1 everywhere in here, so 10, 11, 12, and so on. Right? It's 1 everywhere in here, so between 100 and 200, the first digit is always 1. Right? And that amount of time is greater than the amount of time that the process spends in the in digit number 2, and that's greater than it spends in digit number 3, and so on and so forth. Right. So that is a possible explanation of Benford's law. Now, that is true only for sort of nicely growing exponential quantities, but Benford's law is an empirical law. Right? It's not something you prove, it's something that you observe in the data. And you can do it with a bunch of different data sets of numbers, and I think you will actually get to do it in one of your labs. And you will see that, yes, pretty much that is true, surprisingly, many times. It has some nice applications as well. So people have used Benford's law to detect forgery in data sets. Right? So if you take a collection of naturally occurring numbers, it fits Benford's law pretty well. If you start messing around with the numbers, you know, in various ways, if you mess up, if you mess enough numbers, they won't fit Benford's law anymore. So it's there was at least one example where this was used to detect falsification of numbers.